go over this math.
No matter how permuted up your minds are, they can be restored using at most 2 extra players.
Okay, so what's the situation? What's the math that they're trying to solve?
Okay, so I think the problem is they have the mind swapper.
Yep.
So they have bodies and they can swap the minds and the bodies.
Yep.
So they want to swap everybody back to the original,
original
mind,
the original
to the
bodies.
body.
Yeah, but there's a rule that you can't swap with the person that you've already swapped with.
That's right. So I thought initially like you could just reverse all the swapping you did and then you get back to normal. But you can't do that because you can't reverse swap.
Right.
So the question is, how do you get back to normal? Because you can't swap, you can't do a reverse swap. So once A goes to B, B and A swap, they can't swap back.
Mm-hmm. And if you introduce C, well, then you can go A and B, then B to C, and then C to A. But then now you have a problem again where C to B had already happened once. So you can't do it with 2. You can't do it with 1 additional person.
1. Right.
I think you need to have an even number of people, which is 2.
Mm-hmm. So I think you were telling me this is an actual theorem.
Sure is.
That what is it called again? It's
on this page. It's the Futurama theorem, named after this episode. I guess it depends on who you're talking to. They call it different things.
Theorem. How do you spell theorem? Theorem. There we go.
Yeah, so in 2010, David X. Cohen revealed that...
Here we go.
David X. Cohen revealed that the episode written by Ken Keeler, a PhD mathematician, penned and proved a theorem based on group theory and used it to explain the plot twist in the episode. Keeler doesn't think it's so humble. So humble. Keeler doesn't carry enough weight to be called a theorem, calls it a proof. And then another person says, we should call this the Futurama theorem, Alexander Bogolamny. And then a mathematician, Grime at the University of Cambridge, calls it the Keeler's theorem.
Mm-hmm.
Yeah, so I guess it's the theorem that solves this problem, like made from this episode, became an actual real theorem. That's super cool.
Super cool. And what is it? The problem statement is you have a bunch of people mix up their minds, but you can't reverse. You can't go back directly. Mm-hmm. So how many people do you need to introduce to be able to go back
to untie
the original
that knot.
configuration? Untie the knot.
And apparently
the answer is 2 and 2 only, which is surprising.
Why is that surprising?
Because I would have thought it would be 2 or more, right?
Okay.
I can always
so I guess my thoughts was an even number, which would be 2, 4, 6, 8. What you're saying is that the answer that they provide is 2 and only 2.
See what they say again.
No matter how permuted up your minds are, they can be restored using at most 2 extra players.
So he says at most 2 extra players. He doesn't say at least 2 extra players.
Right, that's specific language.
Right.
Okay. Okay. I think I got it. Okay. So I think it's at most 2, because if I were to introduce 3, well, that violates that I need an even pairing. So which means I go to 4. If I go to 4, well, I can use group theory, and I can map that back onto the previous problem. Like if I had 50, I add 2. If I add 4, I take these 2 and I absorb them into the 52, and then I'm back to the original problem.
I see. So if the more you introduce, you can just redo the problem with a higher number.
Yes.
So there's really only a need to introduce 2.
Right.
Introducing more than 2 just reframes the problem to a higher number.
Exactly.
Okay. This is really cool by Futurama.
That's really good, right? Right.
Yeah. Super cool.
Put PhDs in behind writing cartoons. Good stuff comes out.
Okay. Now that I actually want to read this theorem, but I'm not going to do it now, but I'll actually read it. It's kind of cool.
Yeah. Sounds good.